All right, guys, welcome to another episode of CUDA Education. I already did sort of a first video on the shader binding table and just trying to figure out all the moving pieces with it. This is my second attempt at the topic, and my basic approach now is just to kind of go over the code line by line, um, and investigate things and figure it out, and revisit, go over it again and again and again, maybe cover some other topics and then come back to this, and as we build our understanding of Vulkan, we could sort of learn in the process, right? And you could follow the Vulkan API series, and learn along with me, and you know and build yourself up and your understanding. um so of course I always have to do my little plug. So if you wanna be able to run these examples here, right? All of these examples, you need to get tutorial number 1 and then tutorial number 13. So tutorial number 1 is installing the Vulkan SDK, and tutorial number 13 is installing these examples here, right? So you have all of these examples here. You could only run the ray tracing examples if you have a ray tracing capable GPU on your system. So the tutorials that I'm talking about assume, number 1, that you're on a Windows machine, and that you have a Vulkan-capable GPU on your system. And then for the ray tracing examples, that you have a ray tracing capable GPU on your system. In the case of NVIDIA, you need to have an RTX or greater GPU, so you could get the ray tracing capabilities. You could get those two examples, or you could get the whole series. I have a whole series on Vulkan, and I'm basically picking apart an example, um, and basically walking you through it. So so I do everything. So the CMake stuff, the setting up Visual Studio, downloading the SDK, all of that, right? So I do it just like how I do here, where it's kind of simple and straightforward. There's no programming knowledge assumed. So I'm basically assume that you've never really used a computer almost, right? So yeah, so if you want to join in on this, definitely. So here is our ray traced triangle, right? And we're trying to pick apart this example here. um so I definitely encourage everyone to get on board. Okay, all right. So we're on this shader binding table situation here. Um very first line of code in the shader create shader binding table function is uh shader group handle size. So there's a ray tracing pipeline properties, shader group handle size. Okay, so we have VK, physical device ray tracing pipeline properties, KHR, and there's this shader group handle size. Okay. Um, Now if you put in, let's go back to it. If you put in this into Google, right? The spec is gonna come up, and then the spec is gonna basically, it has all the parameters, and the third parameter that it outlines is the shader group handle size. And what it says is the shader group handle size is the size in bytes of the shader header. Okay, so now we're dealing with the shader header, right? um what is that? Okay, so then you go back to Google and you type in shader header, right? And then basically what Google says, or what our friends at NVIDIA say, um, it says first 80 bytes. Okay, so first 80 bytes. The first 80 bytes of a GPU program known as the shader program header, SPH, contains information about the program which the GPU uses to determine how to execute the instructions. Okay, so that's a little bit of knowledge. Okay, so so we're dealing with the shader program header and how the information that the GPU needs to use to execute the instructions. Okay. Okay, and then there's more information that is sort of communicated. Um, is this from NVIDIA though? Hold on. Okay, so anyway, so it says SPH overall structure. Some portions of the SPH are interpreted differently depending on which stage of the pipeline the program is used with. Example, vertex or fragment. Whereas some portions are always interpreted the same way, they are common for all program types. I don't want to kind of dive too deep into it more, but let's just at this point run with the fact that the shader group handle size deals with the shader program header, which contains information about program, which the GPU uses to determine how to execute the instructions. Okay. Don't want to dive too much more into it. Let's just leave it at that for now. But do know that this VK physical device ray tracing pipeline properties KHR needs this shader group handle size. Let's look at the top level definition of what this VK physical device ray tracing pipeline properties KHR is. So in the spec, it says basically it's the properties of the physical device for ray tracing. So I'm going to assume that what it's talking about, of course, is the GPU, the ray tracing capable GPU that we're using, right? So physical device generally means, you're talking about the GPU. Host, of course, is the CPU. So so properties of the physical device for ray tracing. Okay, so we initialize this variable that basically takes, gets a shader group handle size for this guy. And now it has moved me from where I was investigating. Okay. And notice, just while we're on the topic, VK physical device ray tracing pipeline properties KHR. Notice that there are other things: max ray recursion depth, max shader group stride, all this other stuff. But we're not going to get carried away. All right. So the next line, handle size aligned. We could dive into it, but basically we know that we're doing something with the shader group handle size, and we're sort of just managing it to make sure that everything lines up properly, right? Let's dive in, guys. There was something else I wanted to. All right, so our aligned friend right here, right, is basically Vulkan Tools CPP, right? So it's this guy, which I'm not going to get into, okay? But just know that we're trying to manage this shader group handle size thing here, and it has to be aligned. Group count, still managing this situation. And then our SBT shader binding table size is the group count times the handle size aligned. Okay. I know this is pretty important, so just be mindful of how this was built, right? Because this shows up a lot. So it's a group count times handle size aligned. All right. Um, so now we have a little lowercase vk, so we know we have to pay attention to this guy here. Okay, so a vector is initialized, shader group handles storage, SBT, right. And of course, when we go to the definition, that it's this guy, right? So we create a vector, and then now we drop into this lowercase vk, get ray tracing shader group handles KHR. Okay, so you know what we're gonna do, guys. We're gonna drop this. Well, we could do this too, but we're gonna drop this into Google VK. Right. All right. That's just initialized. So we're gonna drop this into Google and see what pops up. All right, let's see what pops up when we do this. Okay. VK get ray tracing shader group handles KHR. Query ray tracing pipeline shader group handles. Okay, to query the opaque handles of shaders in the ray tracing pipeline. And then it has its parameter list, which basically reflects here, right? So we have the device, which is the GPU. We have the pipeline, which I guess we're gonna stumble on this at some point because um, we haven't covered that yet. The next parameter is the first group, which is 0. We have for 0, and then the group count, which we have up here as our friend, right? Shader group dot size, right? The group count, and then we have our SBT shader binding group size. So in the spec it says data size, right? So that's the data size. So like I said, this SBT size thing comes up a lot, right? So that's this guy here. And then shader handle storage data. Okay. It has type void p data. Okay, pointer data. Right. So that's the data. Shader handle storage data. Okay, so let's dive into this. Um, right. I do want to see. So yeah, I'll need to spend more time with this guy here. Shader handle storage data. So it's a vector. Into this. Okay, so this guy is very interesting. So you notice we're creating 3 tables here. But notice that each table is adjusted based on alignment, right? So we have our shader handle storage.data, but then these alignment handles, right? This handle size alignment is changing exactly where what is readed, right? So this has something to do with the offset, the alignment, all of that stuff. Don't want to get into it in this first run. I'm like Vulkan. I do render passes, okay? So we're gonna revisit this thing once we learn more about what's going on. But basically, notice here that so for the RayGen shader binding table, which is the first table, it's just the data itself. But then for the second one, notice that we're just where we're mem copying or where we're reading by the handle size aligned. And then for the hit shader binding table, so this is the mist shader binding table. We do one stack of, or one cohort of handle size aligned. And then for the hit shader binding table, we do the hand size aligned times 2. Now, I would like to add my contribution to this discussion, and you guys should know this. Orders of operation. I really think there should be a parentheses here between these two guys, just to force the system to make sure that you multiply handle size aligned by 2 before adding this piece of it to it, right? Even though the system might know that, like, you do multiplication before addition, you can't always guarantee that. So that is my definition to the discussion. Orders of operations, guys. I think the system would already, heed to that. I don't really want to put my parentheses here because I might crash the program and embarrass myself, but that's all right. Anyway, so that's this guy right here. So again, the definition for VK get ray tracing shader group handles is query ray tracing pipeline shader group handles, right? So that's that. Next thing that we're going to this VK buffer usage flags. Okay, so it's just a bit mask for VK usage flags, which, we got all different kinds of flags, right? So basically, I'm gonna, I guess we're just flagging that it's a shader binding table, right? Let's just do our due diligence just to make sure. Right? So that's that. Okay, so I'm just gonna go through something that came up. This is part of the um, it says buffer device addresses a very powerful and unique feature to Vulkan, which is not present in any other modern graphics API. Congratulations, Vulkan! You're doing such a great job. The main gist of it is that it exposes GPU virtual addresses directly to the application. Okay. And the application can then use said address to access buffer data freely through pointers rather than descriptors. Okay. What makes this feature unique is that we can place these addresses in buffers and load and store them inside shaders with full capability to perform pointer arithmetic and other fun tricks. Okay, so that's um, when you Google this part, it comes up in sort of the spec. Um, VK buffer usage shader device address bit. So I guess it's a convenience feature. It might also be an efficiency feature because now you're going directly into the GPU virtual address as opposed to, going through the step of using descriptors. And we know what descriptors are, right? Descriptors are basically um, things that describe things in memory. So you don't hand over a blank USB stick. You actually label what's on the stick and what is contained on the USB stick. So um, that's this guy here. I'm just gonna say this is just describing that it's a shader binding table, right? Memory usage flags. Okay, so I'm just gonna do the process just to do it. And okay, so I know from previous experience that this is host making whatever memory we're working with visible to both the host and the GPU. So it's like, and anytime you see this coherent bit thing, you know that it's like the GPU, the device, and the host CPU. So the host and the device, or the CPU and the GPU, uh, can sort of have access or see this piece of memory, right? That's my contribution to the discussion. Um, and then now we create the buffer. Okay, so Vulkan device, um, create buffer. So buffer usage flags, which we're inheriting from here, right? Memory usage flags, which we're inheriting from here, and then raygen shader binding table. Okay, so this is our handle. Um, This is what we use to refer to the raygen shader binding table, right? So that this is the label, right, for that. And then the handle size. So the handle size is this guy up here, okay? So remember we did that. That's a shader program header, blah blah blah. Handle size, okay? So for each of the shader binding tables, um, we do this create buffer thing, right? So we have our raygen, our mesh shader, and our hit shader. Notice that I'm going to assume that all these tables are the same size, right? So there's no difference between the raygen shader binding table, the mesh shader binding table, and the hit shader binding table. And and I'm going to assume now that basically these tables are now created, right? I was hoping for a little bit more, something a little bit more special, like a lowercase vk thing, but no, there's no lowercase vk. We just run this. We just create the buffer, right? I guess it's just a table, so it's like a container, which makes sense. Um, and then of course he does this vk check result just to make sure that nothing crashes. Remember, this example is being used on several different systems, right? So you can't always assume that all of our systems are exactly the same. Um, you also don't know how far into the future people will be running these examples. So you don't, technology will change, and things will be implemented differently and all of that stuff. There might be new device form factors, all that. So we have to do a VK check result for all of these things. Okay. Um, so let's just I just want to see where this raygen. I'm really, you know what? I'm really excited about the raygen. Like the mist shader and the hit shader is cool. Yeah, but I want to generate some rays. Okay? I want to be like Raiden in Mortal Kombat. But I digress. I want to generate some rays, man. Come on, show me how to generate some rays. All right, so I want to see what this raygen shader binding table. I just want to see where else it is referenced. All right, it's referenced in the command buffer. It's initialized. Okay, so it's initialized here as just a regular buffer. And then, of course, we destroy things once we're done with them. That's it. 900 lines of code, and you only reference it a couple times? Come on. Raygen is the coolest thing. There's nothing greater than Raygen. Like in all of this script, the Raygen thing is like the coolest thing. Just letting you know. All right, so we created here. We do another memory operation. That's fine. It's part of the command buffer because of course we have to do stuff. Right. Yeah, we'll get to that. And then we initialize it. Okay, so that's it. All right, so that's Raygen shader binding table, and then I know some of you guys prefer the miss shader binding table for some reason, so we'll just go through that too. So it's the same situation, right? For all of them, right? Hey, you know what? I know the haters, they like miss shader binding table. Yeah, that's right up their profile. The haters, man, they like when things miss. Anyway, similar situation. Okay, so I'm inclined to stop here. I mean, I'll go through this a little bit right now. So copy handles, this is just some kind of memory operation. Mem copy, it's just some kind of memory operation. But I do want to reiterate again this little piece right here where the first table is just the shader handle storage data itself, and then the miss shader binding table is the shader handle storage data and the handle size aligned, just adding one piece of it. And then the hit shader binding table is the same thing, but you're adding two pieces of handle size aligned. So it's two pieces of handle size aligned. You're adding to the the shader handle storage data. Okay, and that's how you differentiate one table from the other. So it's sort of like a memory offset or a memory aligned kind of thing. And that's my contribution for today, guys. I don't want to get into more stuff because I think we need to let this kind of settle in our minds, and then we'll move forward again. So just to do a quick recap, the shader group handle size is part of the shader program header, which is 80 bytes or so initial bytes that the GPU uses to figure out how to execute the program, right? And then, right, we get our shader binding table size, which is, a combination of all of this right here. Okay, so the shader bindings table size is important. We have a lower VK function, get ray tracing shader handles KHR. That's basically, I guess you're communicating to the application what exactly, what is the whole story of this thing, right? And of course, you could Google this and look at it in the spec. This guy seems to be pretty important. Okay, so this last piece here, shader handle storage, right? And it's just a vector, but yeah, it seems to be a big deal, right? And then we have some buffers, and the buffers have flags, so we're declaring that it's a shader binding table. It's supposed to have shader binding table information, and of course that the shader now has device information in the GPU, which is supposed to be more efficient way of doing things and more capable way of doing things than going through the descriptor set situation, right? If anyone knows the backstory behind this piece, apparently it's a big deal. Vulkan says it's specific to them. So shout out to the Kronos group for their for their innovation. And then we have our memory properties flags. So, this just means that the GPU and the CPU can see the memory here. And then we create our shader binding tables. It's just a simple buffer operation, right? All right, let's actually, while we're on the topic, let's just dive into it. So this create buffer thing, right? So create a buffer on the device. Now, when it says device, you're talking the GPU, right? Anytime you see device, GPU. Anytime you see host, it's the CPU, right? There's two worlds in the application, just like how there's left side of the brain and right side of the brain. Same thing with Vulkan. So create a buffer on the device. Usage flag bit mask for the buffer, right? Index, vertex, whatever. Memory properties for the buffer. Buffer pointer to the VK Vulkan buffer object. Size of the buffer in bits. Pointer to the data that should be copied to the buffer after creation. Optional if not set, no data is copied over. Okay, so that's pointer to the data that should be copied, right? So pointer to the data that should be copied. Okay. Return success if the buffer handler and memory have been created and optionally pass data to whatever, right? So I was Visual Studio is just like they're always introducing new stuff. So there's this GitHub Copilot thing where they're using AI and stuff. Interesting things. Anyway, all right. So so that's this guy right here. So it's just creating a buffer. I was thinking it's gonna be more special, but I mean it's just creating a buffer and all of that stuff. I do want to generate some rays though, so I want to figure out how to generate the rays. I want to generate rays. I want to generate a whole lot of rays. I want to generate a little bit of rays. I want to see how the scene changes with different amounts of rays that are being generated. I want to see if the GPU buckles because I'm generating too much rays, or if it if the fan comes on, if just different things. I want to generate some rays, man. But yeah, we're gonna stop here. And then I guess the next video will be talking about create the descriptor sets used for ray tracing dispatch, and we'll tackle this piece right here. But yeah, I think that's enough for this video. Oh, we're gone 33 minutes. So anyway, guys, again, if you wanna be able to run these examples on your system, on your Windows-based system with a Vulkan-capable GPU, definitely get tutorial number 1 and tutorial number 13. I will have those in the description below, along with the entire series. Get your friends together if you're artistically inclined, if you're creative, if you if you want to do cool stuff, if you want to do simulations. It's not just video games, guys. It's not just video games. It's business related stuff. It's simulating engineering. um you know uh you're doing CAD, you're doing just you need to be able to put pixels on a screen. Okay, so the video game stuff is cool, don't get me wrong, but you know it's future proofing yourself so that you'll always be relevant, and you'll always be able to add something to the table, and data analytics, all of that stuff, right? Not just a spreadsheet, but you have you could actually visually see the data, right? Because you're visually representing the data that's coming through, right? But you have to be able to put a pixel on the screen. So get your friends together. I don't recommend you doing it alone. I think you need to have a group of your friends together. And I assume no, you see how I'm diving into all of these topics here. I assume no programming knowledge whatsoever. Okay, So even with installing the Vulkan SDK and installing these examples here, I literally walk you through it. I share my screen and I walk you through. Um, I share my screen and I walk you through the how to set up everything. So definitely check it out. Um, get your friends together and work through it. I'm working through it myself. It's a lot of concepts. It's a lot of definitions. It's a lot of implicit assumptions in Vulkan. No fault of Vulcans, no fault of Vulcans. The reason they do this is because they want to give the programmer control over everything that's happening in the GPU and in the application and on even on the CPU side and everything. So yes, it's a lot of work, but it's necessary. And once you get the handle of how to create a triangle, everything else sort of becomes easier. It's like because you have a basic foundation of why things exist and what's needed to be done if you want to move on from a triangle and do more special things. So um I've focused more now on the ray tracing stuff, because that's like the really cool stuff. That's like real time, really generating a scene, not just like showing pre-processed stuff that like an artist created. So the shadows show where they should be shown. The colors in a scene are basically an amalgamation of all the rays, um, and all the other objects in the scene, so it looks very photorealistic. You creative guys know more about this stuff than I do, but ray tracing, guys. So it's been all the rage. Everyone is running their video games with it. Everyone is getting GPUs for it, but I want to learn how to actually do it. So that's why you hang out with CUDA Education. Stay away from the haters. Don't drink haterade, okay? Don't drink haterade. Stay away from the haters. If someone comments whatever, you do a comment that says this tutorial was really helpful and all of that stuff, okay? um yeah, guys, thank you for watching. Have a great day. Tomorrow, or in the very near future, I will continue on the path of our first run through this code. um there's a lot to cover, so that's about it. Three shader binding tables: rage, and miss, and hit. Have a great day, guys. Bye.